Hi, everyone. Wow, these lights are bright. Everyone gets up here and says that. They're not kidding. How do you do? My name is Bernadette Highland Wood, and I think this is just incredible having this event here. As you can tell from my accent, I'm not from here, but I live here. And I could never get into one of these conferences in the US, so I had to travel 9,000 miles away to come to one. Kidding. I am actually one of Brisbane's first web product development companies. We set up shop here in 1995 and have spent 10 years back and forth between that time in Brisbane and the United States. Most recently, I was in Washington, D.C. But with the new occupants in the White House, I vacated. So I have the distinct pleasure of introducing a fellow PhD candidate in electrical and computer systems engineering from Monash University. I'm at UQ. She's going to illuminate us on visible light positioning. And Stephanie Sincata is knocking it out of the park, already having 2 peer-reviewed academic published papers, and she's traveled to France and the UK to present her research. And an interesting fact that I just learned is that she has 2 rescue greyhounds. And I want to kind of just set the note here about this is that it's very brave to come up here when you're a PhD candidate or speaking for the first time. And I just shared with our second speaker, Tan, that 24 years ago, I was sent by Sun Microsystems up to James Cook University to talk on the future of the World Wide Web on education. You know, the web was really new then. I had just come from Silicon Valley. And I was so nervous, I had to go up to the podium with my partner because I had hives all the way up to my neck. Now I'm very comfortable speaking in big groups, having done it many times. But I just want us all to sort of send some supportive, warm energy to both of our speakers. Stephanie's apparently rather experienced at this, but Tan, this will be her first time speaking in public, and I'll introduce her in a moment. But let's give Stephanie a big, warm round of applause.
Hi, I'm Steph, and I guess you're all here because you get lost indoors, and so we've got a solution for you about that. So the introduction pretty much covered everything I was going to say. So I'm a PhD candidate, and my supervisor, one of them is here in the audience, Jean Armstrong. You might have heard her speak earlier today. So I've been working on positioning for about 6 years now, since I was an undergrad doing a research project, and since then Jean hasn't been able to get her claws out of me, so I just keep doing it. And so I've done some publications already, and I presented last year at the big indoor positioning conference in France. We'll be doing that again this year in Pisa, Italy. And I was tricked into going to Warwick and Oxford when my supervisor said, why don't you go and visit them? And I thought she literally meant visit. She meant give 1-hour seminars, so that was an interesting experience. So just a quick outline of what I'm going to be talking about today. I'm going to talk first with just an introduction to indoor positioning. We often get the question when we start talking about our technology of, well, why would you want to do this? So hopefully I'll be able to motivate the topic there. And then I'll talk to you about our technology and the evolution of how we got to where we did. So starting with our first receiver structure, we call this the Quater, and then how we improved on that with our hybrid receiver structure. And finally, just some extra points on how we implement this to be a very robust system that works. So why do we need it? This is a really common question. And I guess there's a lot of applications, and perhaps the most obvious one that you can think of is indoor navigation. So we're all kind of used to using Google Maps now or something like that to get out and about with our GPS. And what we notice is that when we get indoors, it doesn't really work. So it'd be really nice when you're going out and about into the shops, big shopping centres like Chadstone we've got down in Melbourne. I'm sure you've got something else up here. To be able to find our way around really easily, and those retail services would just love to advertise to you and know where you are as well. But there's other applications as well in warehousing, asset tracking, robots as well. So this is a really big field, and it's estimated to be worth a large amount of money as soon as somebody does it, right? So there's a lot of market research, and they're suggesting that the barrier here is that no one's really come up with that killer technology, and we think we have it. So what are the challenges here? So as you know, GPS doesn't really work indoors. If you look at the bottom picture here, this is not obviously clear, but this is actually taken at my desk at Monash. And it suggests that I'm actually in about half of the building. I'm actually on the second floor and in a very specific location, but GPS can only tell me I'm sort of in about half the building. And this is in a room with windows, so there's perhaps some line of sight to satellites, maybe not much. So even where it is available, it's really not accurate enough for any sort of indoor applications. And so just like any positioning system, and here's the original visible light positioning system, the lighthouse, we need some sort of beacon to transmit our signals. And we need receivers that are capable of not only sensing those signals, but also knowing something about where they came from. So we need solutions that are accurate, and that doesn't necessarily mean very accurate always. So this is an application where if I'm standing in front of the wall of Coke at Coles, I probably don't care if I'm here or if I'm over here. But there's a lot of applications where that's not acceptable, especially in drones and robots and all those sort of tracking applications in industry. But we also need solutions that are economical for businesses to be interested in them, so scalable, low maintenance. And we also think low additional infrastructure is really important. So there's a lot of ways we can achieve this, and most people have been working in using radio frequency methods for a very long time now. The problem with radio frequencies is we have multipath problems with reflection, so it's very hard to know where that signal came from. And so sort of the best accuracy people are achieving are, in a really good case, 1 metre, but usually several metres. And if you look at the top picture here, this is actually a system that's actually in place in Gatwick Airport in the UK. And they thought it was a really good idea to spend millions of pounds installing 2,000 battery-operated Bluetooth beacons. So I think they'll have fun updating that in the future. So we don't really think these are particularly good solutions. And there's a lot of other methods people have tried. Most of them seem to revolve around fingerprinting. And fingerprinting means that you go around and take all these measurements offline beforehand, store them in a database. Then you need to do a lookup later to find where you are to match to this database. If anybody moves something or changes something, the entire database changes. So maybe you need to update that using cloud services where you're pushing your data back and people are tracking you. And these are sort of not very robust features and not things that we're really interested in. So we think that the best way to do this is using visible light. So visible light positioning is an interesting technology. And it's mostly come about because we can use LEDs. So most lights now are being replaced with LEDs. They've got a lot of fantastic features. They're energy efficient. And the thing we like most about them is that we can switch them very fast to transmit data, and we call that visible light communication. And so once we're transmitting data, we can transmit the position of our lights in the room. And you can see here the little person standing there, and he's receiving data from multiple of the luminaires, we call them, which is just a fancy word for a light fitting. And therefore, he's able to work out his position with his receiver. So there's a lot of ways we can do this. And probably the most common one that we see a lot of is received signal strength, where people try to estimate how far the lights travel to them. And this sounds great in theory, but if you make assumptions about the transmitted power, then if anything changes, like the light ages or they get dirty, then that doesn't hold anymore. And so no longer is your information very accurate. So we think that angle of arrival is actually probably the best way to do this. So we've been focusing on that in our work. So we've got these LEDs, and they're flashing away faster than you can see, don't worry, nothing like that. And they're transmitting information about their position in like a global coordinate sense. And we need receivers though. So typically there's two options. You can use a photodiode, which is basically a light sensor. And they're really good because you can receive very high speed data with them, and that's great. But if you want to estimate the angle of arrival, you need some way to determine that. And the way people have been trying to do that is making a 3D structure, like a pyramid or a cube, and putting the photodiodes facing in different directions. And that works, but if people aren't going to accept a camera bump of less than 1 millimetre on their phone, they're probably not going to accept a pyramid sticking out the top of their phone. So it's not really a very good idea. So people have tried using cameras. So I'm talking literally like the front-facing camera on your phone. And this can give you really accurate sort of information about the angle of arrival, because we've got very high pixel cameras now. The lenses are getting very good. But it's very difficult to receive the modulated data. Your camera's probably got a refresh rate of 30 frames per second, maybe a little bit faster if you've got an iPhone or something. But that's not really fast enough for what we need. And there's some workarounds, but they're not very good, and you can't really transmit a lot of data. So this is sort of the bit of the puzzle that we've got to solve. And realistically, what we're trying to achieve here is we want something that's sort of compact, low power, planar, and because we think we should be able to implement these into future mobile phones, or also into sort of compact standalone receivers that can be used in many different applications. So we came up with this receiver called the Quader, which is a quadrant angular diversity aperture receiver, and it sounds very fancy, but basically what we have is a quadrant photodiode, which is up here, and it's quite difficult to see what that is, but it's actually a photodiode that's being cut into 4 separate photodiodes. So there's this very narrow gap separating them. And these are typically being used in a lot of sort of other applications with lasers and things like that, but we're the first people to use that in this sort of situation. And what we do is we put an aperture over the top of it, like you can see here, and that gives us directionality. So when the light goes through the aperture, depending on where it came from, it falls on the quadrants in different ratio amounts. And as long as we receive that light on all 4 of our quadrants, we can determine the angle of arrival. So we also have this sort of height that we can separate these 2 planes by, and we can alter that depending on our needs for the field of view of our receiver. There's trade-offs here. We obviously would like a large field of view. We want to be able to see a lot of the ceiling, but at the same time, that will reduce our accuracy. So, and the important thing here is this is quite planar. This is very much in the same sort of scale as the front camera in your phone. It's quite small. We've got diodes at the moment that are about 4 or 5 square millimeters, so quite compact. And you'll see later on what our current prototype looks like. So I keep talking about this angle estimation, and what angles am I actually talking about here? So when the light hits our receiver, there's 2 angles we're interested in, and the first one's the incident angle, which is this one here. So that's the one that the light makes with the normal. And the other one is the polar angle, so you can imagine it's sort of going around in a circle around there. And you can see there I've got all these X's and Y's and D's and things that I want to be able to measure to be able to figure this out. So what I need to know is I need to know where that light spot fell on my diode, like where the centroid of it is. And we do that using some ratios of the currents that come out of these diodes. So there's 4 separate diodes. We get 4 separate signals. And we're sort of looking at how strong each of these signals are relative to each other. We don't care about their absolute values like the received signal strength did. We only need to know about their relative values. And when there's no noise in the system, this actually really nicely simplifies down to just the ratio of our overlap areas, which makes it really easy for us to make an algorithm to invert this and get back out the X and Y values. So if we know that center and we know that height because we designed that height, we can now figure out all that information we need there. And if you have that information from 3 different light sources, you can triangulate. So this is an animation that took me entirely too much time and probably may not be overly obvious, but hopefully it works. So, all right, so we've got the light spot and the overlap areas coming down. So on the top, we're estimating Y between the top and the bottom sort of halves, and then on the bottom, on the right, the bottom there, sorry, is X, which is using the left and the right. And as you saw, as we moved around, those overlap areas were all changing, and the ratio values between them were all changing. And the important thing in here is that for every position, there's a unique ratio that happens, which is what allows us to be able to determine those centroids that we need to determine the angles. So we did an experiment with this quite early on, and this is our first attempt to make one. So our transmitter is just that single white LED, so it's not very powerful, so we can't transmit a large distance. And our receiver is this Franken disaster here that is made out of 3D printed plastic, which is holding our aperture, which was cut out of automotive vinyl using our vinyl cutter and held over this circular quadrant photodiode because we couldn't get a square one at the time. So this was definitely some creative thinking to get something to test this all out. And so we could move in 2 dimensions only because we didn't have the optical parts to move this in the sort of changing their height relative to each other, because we got all our optical bits from Telecom when they became Telstra. So we're living in an imperial metric Franken-Mount world there with 3D printed parts in between. So if anyone wants to give us money so we can buy better equipment, please do. And so we're moving our transmitter across on the red line and our receiver on the blue line. This allowed us basically to estimate our incident angle. And we needed this manual calibration process where you had to align everything. We had to do a lot of testing just to be sure that we'd align things as best we could. And these are the results we got. So basically, all you really need to know from these results is that the black line is what we simulated and the coloured lines are what we got from our measurements. And as you can see, I apologise, these are all on different scales, so it's not overly obvious to compare them. But what you can basically see is that we are following the same trends there, and whilst it's not perfect, there was clearly some potential here. So we went on and did some more simulations where we weren't just looking at how well we could estimate angles with this receiver, but how well we could then position with that. So this was the best case scenario where you've got 4 LEDs and they're nicely positioned so that everything's really easy to work out. And we model these as a point source. And when I say a point source, it's like the light is coming from just this like infinitely small, tiny point. And that's not real. If you look up, these lights aren't really small. They're quite large. And then we transmitted quite a high optical power, and we had a very short distance between them. And we averaged over many, many samples. And the results looked great. And it looked like we got these mean errors down in 0.2, 0.1 centimetre, depending on if you want 3-dimensional or 2-dimensional positioning. And out in the corners was getting a little bit larger, with sort of 1 centimetre errors. And this all looked fantastic, but this wasn't real. And this was very obvious already. So we thought, well, what is real? And we're the first people to sort of think about the fact that the luminaires that you see out in the world are generally quite large, especially in large buildings. If you look up in this room, and I've already spent some time looking up in this room, there's some round LEDs, but there's also these big square ones, well, luminaires. I don't know if they're LED yet. I hope this building is friendly and uses LEDs, but who knows. And so these big square ones, big batten luminaires, linear lighting, this is very common out especially in large buildings and the kind of applications we're talking about. So we started looking at how that would affect us. And so I think these simulations are all based on a 30 by 30 centimetre luminaire, so quite small, realistically, in the grand scheme of things. But we kept all the other sort of parameters the same. And these pictures down here are a bit hard to see, but this is just kind of, what you're basically seeing is when things get red, they're getting bad. And this is, without any noise, we're seeing that our angle estimation is starting to have some effect just from these lights not being what we expect them to be. And so how does this impact on positioning? Well, this is sort of the impact it makes. And in the top 2 pictures there, we had that same scenario before, but now we've put those larger lights in, and we're seeing that the errors are getting larger. And then we made the situation a lot worse. We made our room larger. We made the height between them bigger. And now errors are starting to get up to 10, 12 centimetres out in the corners. Not as good as we were hoping for. So, and this is just in simulation. You've got to remember there's still other things that can go wrong in the real world that aren't considered in our simulation model. So we've got this receiver that shows, depending on your parameters, that we can have some good performance, but we know it's sensitive to fabrication imperfection, and we know it's sensitive to the size of these luminaires. And it's also sensitive to the transmitted power, which is limited by your lighting standards. We're not asking the room to blind us like those lights are blinding me right now. We're trying to work within a situation where you wouldn't even know it was happening. Wow, we're going to have to speed up. Okay, and we were having to average over many samples, and here's the terrible things that'll happen if you don't. So we came up with this receiver, an improvement on it, and basically what we did is we keep the equator and we add a camera. And so this is our new sort of receiver idea, and this is just a picture I've drawn. This is not it in reality. And the idea is that we can now use the equator to receive the high-speed signals and the camera to do the accurate estimation of the angles. And we can use them together basically with some algorithms. And you'll get much better accuracy sort of down in the sub 5 centimetre range. And so I'm just quickly going to talk about what these reference points are and skip over the next few slides because I want to get to the part about our prototype. But basically the idea is that what we can do now is we can define these points within our luminaires because they're quite large that the camera can detect, and they don't necessarily need to be things you can see. They could be a blue LED, but it's only blue enough for the camera to see, not for you to see, and things like that. And then what we can do then is we can co-locate more than one of those on a large luminaire. And suddenly this requirement to have 3 lights in your field of view becomes 1. And so this is an incredible breakthrough, because this makes our system so much more flexible than many others where the field of view requirements are really tight. So I'm just going to skip this stuff. This is interesting stuff. Come talk to me about it afterwards. But this is justifying how we can get away with this and why it's really good. But this is the really important stuff, is that we're actually making this. This is not just theoretical. This is really practical. And this is sort of our early plan, where we had to design, we had to get someone in to design some luminaires for us. We told them what we wanted, but they were an electronics expert and they did some amazing work for us. At the same time, we also had to get our receiver designed. So we went down to Bunnings, which was a really embarrassing trip with Jean, I have to say. And we bought a whole bunch of these sort of standard downlights, and we ripped their guts out and basically just kept them for their case and their heatsink. And we had our electronics guy design these lights for us. And basically the magic of these lights is that we can transmit the data with them that we've been talking about, that would be the enabling technology. And we actually got that working just last week. So that was really great. We could transmit across our entire lab some data with this light. And this is our new quater. So it's all on the board. The amplifier is on the board, and our aperture is no longer 3D, well, actually it is still 3D printed, but it's not 3D printed on the crap 3D printers. It's 3D printed at the Melbourne Centre for Nanofabrication. And so it's all very accurately designed to line everything up as best you can when you're making the prototype. We went down to IT and bought ourselves a phone. We got a Google Pixel, which is the latest Google Pixel 3. It's got a nice 97-degree wide field of view front camera, which was really great for our needs. And then we built a room out of, well, we self-assembled. Don't tell OH&S. And we built this room out of aluminium extrusion, and it hasn't got walls yet, but it will. And the idea is that we've got these sort of rails in here, and the really great thing about these rails is that we can change the height of our LEDs. We can change their arbitrary positions. They just hang off these rails, and we can basically have any configuration we want. And this is our test bed for our prototype. So we've got all the bits. We are putting it together as we speak. Our minions are working back at Monash very hard on this right now. So just a quick summary. So we just talked about indoor positioning. We had an overview on visible light positioning, and a bit about our receiver structure, which can be used both as a standalone in sort of industrial settings or standalone systems, but also we one day hope to see it incorporated into a smartphone. And if you want any further reading, I do recommend the top paper there, which is a really accessible paper that was published in Communications magazine, and it's the most highly cited paper on visible light positioning, and that will give you a really great overview of the stuff I've been talking about. The rest of it are just the papers I've been writing in my PhD, and that's our patent that we've got on this system. So please do come talk to us afterwards if you've got any more ideas on indoor positioning, or if you would like to help us with bringing that patent to life. Thank you.
Wow, what a legacy Grace Hopper has left with you. Were so articulate, and that just flowed and was really an impressive talk. Thank you very much, Stephanie. Don't go away. Does anybody have any questions, a question or two that Stephanie might be able to respond to? And it doesn't have to be specifically to her research. Yeah.
So really enjoyed your talk. I just wanted to ask, in your system, how you deal with other objects, I guess, indoors. So obviously inside, it's not just an empty room. We've got a lot of things that cast shadows. Sometimes we'll have windows that bring in sunlight. I'd like to know, I guess, how you plan to deal with those challenges.
Yeah, definitely. I guess for us, our system obviously does rely on line of sight to the ceiling. So that can actually be a little bit challenging with your phone, because people hold their phone like this and basically all they can see is their face. So it will require people to hold it sort of more facing the ceiling when they want to navigate with it. In sort of more standalone systems, like if you're thinking like that forklift that I spent a whole afternoon drawing, that is like that would be sort of in a situation where you sort of see enough of what you want. There were some of the simulations I skipped over. I actually talked about how you deal with this in a corridor, which is obviously a really strange situation because it's very long and narrow. And that was sort of part of why our reference points really augments this system. But certainly indoors are very challenging environments because of all the things in the way. But I guess the idea is if the receiver's pointing up, generally, I mean, I'm probably the only person around here that walks around turning their front camera on and looking at ceilings in buildings. But it's certainly something that you generally notice is that when you look up, you can pretty much always see luminaires, and unless you're really short and everyone's above you, like leaning over you, then you're probably going to be okay to see enough.
I have a question about accessibility. Is this something that could be used to assist with visually impaired people navigating a building?
Yeah, we've had that come up before, and I do think that one of the use cases is definitely accessibility for people with disabilities, in particular vision impaired people. Just sort of another way technology can help improve their lives.
Great, thank you. Any other last questions before we take a quick break, and I will ask you to give Stephanie a warm show of gratitude for her talk. Welcome to the almost last session, but the last before the grand finale. My name is Bernadette Highland-Wood, for those of you who have just come into the room, and it's a real pleasure to be here. I have, in fact, waited 24 years to attend an event where there are more women in STEM under one roof than have ever been in my nearly 30-year career. So this is super exciting. We're going to listen to a speaker speak on a topic that's very near and dear to my heart. I was one of the co-founders of the first commercially supported graph database company. She's not speaking about databases, but she's speaking about graph-based learning. But Tucana Technologies, which started here in Brisbane in 1995, was the first commercially supported by 2001 graph database. And we commercialized that technology, used it in Australia, brought it to the United States, and had quite an interesting application post 9/11 for anti-terrorist threat analysis. The topic has evolved considerably, and since Tucana Technologies was around, CSIRO Data 61 has emerged, and it is a world-renowned leader in data science and routinely consulted with for research for government, business, and academia. And today we have Tan Nguyen Mueller, who will be speaking to us about solving problems arising on social networks and fraud detection. And she's going to share some innovative work by example that she's doing at CSIRO Data 61. And for those who are unfamiliar with Data 61, 61 is the country code of Australia. It's not because we have 61 states or anything like that, but it's the country code for the country. And she's going to be talking about scalable graph-based machine learning. So fun fact, Tan just finished her first half marathon, 21 kilometers, and this is her first public speaking engagement. So please give her a very warm welcome and send her all your energy of warmth and support.
Thanks for the introduction, Elizabeth. And hey, everyone. This is my very first talk today, as Elizabeth just mentioned. So I'm super excited, but also a little bit nervous as well. But yeah, let's get started. So when was the last time that you tried a new restaurant? Did you look at online ratings and reviews when choosing this restaurant? I don't know how you do it, but that's normally how I choose a restaurant. So this information is just a tiny fragment of a vast amount of connected data that we are exposed to in our everyday lives. My name is Tan Nguyen Mueller. I'm a senior software engineer at CSIRO's Data 61. And today, I'm going to talk about an approach on how to use this connected data to solve a classification task at scale. Imagine you are a talented sushi chef, and you just opened a new sushi restaurant. You realize that nowadays, people search for restaurants by looking at online reviews and ratings. So you think that having some online influencers come to visit and review your restaurant would help promote it. Apart from being a sushi chef by day, you are also a curious developer by night. So suddenly you have this idea of exploring the Yelp datasets and build a neural network to discover online influencers who can help promote your business. So now that we have the dataset, and we want to discover online influencers, so perhaps the good place to look at in the dataset is the users. Each of the users in our dataset has a set of attributes that contains information about them, ranging from number of reviews that they have written, as well as whether these reviews are useful or even funny to the others. So we could use this information to predict whether the users are influencers, like the traditional machine learning approach. But each of our users also has a list of connected friends. And maybe when we explore these relationships of the users, we will be able to detect interesting patterns of influencers and non-influencers, such as influencers might have many connections, like many friends, or they may be even connected to each other. So now we know that our data is connected data. Let's imagine this as a graph. So a graph consists of nodes and edges. A node is an entity in a world, and the edges are the relationships between them. For our Yelp dataset, the users would be our nodes, and the user friendships would be the edges. For some of the users, we know that they are influencers, and some that are not. So we can use this information as ground truth for our prediction. And in order to learn the interesting relationship patterns of influencers and non-influencers, so maybe this is a good place to start exploring. Thus, it's to look at the influencers and non-influencers directly connected friends. So we will call this as users neighborhood. Now we know we want to use the node or the users neighborhood for our prediction task. So let's see how we can do this. One way to achieve this is that we will aggregate what we know about the user's friends. So this will give us a new set of attributes about our users that contain both attributes from the users itself, as well as the user's friends. So we don't have to limit ourselves to just directly connected friends, but we can expand the neighborhood such that we can use friends of friends or friends of friends of friends. And in this picture, we see that we aggregate neighbors' information from 2 hops away. That means friends of friends network. So now we have this aggregated information, this new attribute set that contains not only the attributes from the users, but also from the user's neighborhood. And when we use this new attribute set and hand it over to the downstream machine learning task, then it will be able to detect the user's characteristics as well as the relationship patterns of the user's friendships, and use that to predict whether a user is an influencer. So now we know that we can build a neural network that can use nodes neighborhoods for our prediction task. Let's look at one more detail. When a node has many neighbors, so instead of using a full neighborhood, we can take a sample of a fixed size set neighbors. And we can do this by randomly selecting the neighbors. The advantage of sampling is that we don't have to use the entire neighborhood, but just like a subset of our neighborhood. And this will help us limit the computational footprint. And this is also one way to deal with when our data is sparse. So far, we have just looked at an approach of how to build a neural network that take advantage of the connections in our user's neighborhood. And it will use this information for the prediction task. And with this, we can apply any node's neighborhood to generate a new attribute set for each of the nodes and use us to predict whether our user is an influencer. The approach I just described is the graph SAGE algorithm, where SAGE stands for sample and aggregate. And our task to predict a node's property, in this case, influencer or non-influencer, is called a node classification task. So we know that we can use users' informations and also users' friendships for the prediction task. Basically, we could stop here, but we can dig deeper into the data set. And we see that in the data set, it doesn't just contain information about the users, but also information about businesses that the users have written reviews for. It also contains information about the businesses itself, like, for example, number of ratings that the business have, whether a business is trending or not, as well as some information about the ambience of the businesses. So by incorporating this business information into our neural network, it will be able to learn more about the behaviors of influencers versus non-influencers. For example, that influencers might normally review business with high ratings or business that is trending, whereas non-influencers might just try out a new restaurant and randomly review it if they like it. So maybe this additional information will help increase the accuracy for our predictions. So by taking the business nodes into our graph, we will have a new graph with two types of nodes, a business node and a user node. And we also have two types of edges, the user's friendship and the review edge type between a user and a business. So as we have seen in the previous slide, a business has a completely different attribute set than the users, such that business has information about the ratings of the business, or like the ambience information of the business, rather than cute or funny like the users. So we can't really aggregate these two different data attribute sets together like we previously did when our graph only has a single node type, users. So we realized that we have a problem, that graph SAGE only works with a graph with a single node type and a single edge type. And we will call this graph as a homogeneous graph. Our graph with users and businesses is no longer a homogeneous graph because it has multiple node types and multiple edge types. And we will refer to this as a heterogeneous graph. So how can we solve this classification problem for our graphs with users and businesses? Of course, we would like to use something similar like graph SAGE. We don't want to start everything from scratch again. So in a heterogeneous setting, we will aggregate the information of the neighbors similar like we did in graph SAGE, but this time we aggregate for each of the edge types separately. So that means we aggregate the attributes of the users for the user's friendship, and we aggregate the business attributes for the review edge type. We will then concatenate this aggregated information about our neighborhoods of friendships and reviews with the user's attributes themselves. So these new attribute sets hopefully will give us a more complete picture about our users that we can use for the prediction task. So we have just looked at a way to generalize graph SAGE to work with heterogeneous graphs. And we call this generalization hint SAGE. And now that we have worked out how to build a neural network that uses the neighborhood with users and businesses, so maybe let's see how we run that on our Yelp dataset to see if we can discover some online influences. Our Yelp dataset has in total 1.7 million nodes and nearly 20 million edges. Its total size is around 8 gigabytes. So when I run the neural network on this Yelp data set on my laptop with 4 cores and 16 gig of RAM, the job was terminated because it runs out of memory. Why did that happen? The graph is just 8 gigabytes RAM, and my laptop has, the data set just has 8 gigabytes, and my laptop has 16 gig of RAM. So that happened is because on each aggregation step, our graph keeps growing larger and larger. This is because the node doesn't just contain its own attributes, but now it also contains the attributes of the whole neighborhood. So that means that the larger the neighborhood set, the neighborhood size that we use, the more memory we would need. So when a single machine cannot solve our problem, what can we do? We can take, of course, a smaller sample of the neighborhood. But if it doesn't fit onto one machine, we can use multiple machines. So we can scale it out with Spark. On Spark, instead of running the computation for our graph on a single machine, the Spark driver program that runs on a master will split and distribute the computation onto multiple workers in our cluster. And within Spark, we represent our graph with a nodes data frame and an edge data frame. Each row in our nodes data frame contains a user node or a business node. And the edge data frames contains the relationships between our nodes. So that means the source node ID, destination node ID, and the type of the edge, so friendship or review. We want to obtain the nodes neighborhoods that we can use as inputs for our neural network. To do that on Spark, we can join this nodes data frame and edge data frame together, and then we will group by the nodes IDs. And the result of this join and group by operation is that our node now contains its own attributes like previously, but it also contains its one-hop neighbors. So the first 2 rows of this data frame tells us that the user with ID 3 is friends with user with ID 4 and has previously reviewed business with ID 2. In the second row, business with ID 2 was previously reviewed by user with ID 3 and user with ID 4. When we repeat these join and group by operations on the neighbors of our nodes, we will obtain the second hop neighbors. So we can keep doing this to expand the neighborhood. But for this example, we're going to just use 2 hops neighbors. Now we have just prepared a node neighborhood that we can use as input for our hint-sage neural network that will generate the attribute sets and use that for our prediction task. So this would be how it looks like on one machine. And in a distributed environment, Spark will split our data frames into multiple partitions and distribute it to multiple workers. Now, each of the workers also has a copy of the neural network that it's used to train on this partition of the data frame. And then at the end of the training operation, the parameters that it used to train will be average. And the master will have a copy of the trained neural network so we can use for prediction. So with GraphSage and hint-sage algorithms and our scaling methodology on Spark, we are able to process a large graph that wouldn't fit onto memory otherwise. And finally, the result of our models tells us that by being precise 67% of the time, we will be able to discover 86% of influences. So this model that I just run to prepare for my talk, so it isn't tweaked. So don't look too much into the result, actually. So now that the neural network has given us some hints about which users are influencers, so maybe we can take the top predicted influences maybe by sorting them by predicted scores. And then we can go on Yelp and then check out whether they are actually influencers or not. And if they are, we can invite them to our restaurant, prepare an awesome sushi meals, and hopefully they will write some positive reviews. And finally, we have some good reviews, and we are happy. We hope that we are busy enough with the restaurant so we don't have to do some machine learning tasks at night anymore. So yeah, it's time to wrap up. In summary, we have learned that connected data can be represented as a graph, and we can solve a node classification problem by sampling and aggregating the node's neighborhood. We then channelize that with hint-sage to work with heterogeneous graph. And finally, we see how we can represent our graph on Spark with node and edge data frames, and how we can prepare the node's neighborhood by join and group by operations. Then we distribute the neural network on Spark so that we finally achieve a scalable graph machine learning pipeline on Spark. So aside from working on the graph analytics platform, we also have a Python library that contains graph machine learning algorithms. And we are also working on a graph storage, as well as a visualization tool. So the pipeline that we are working towards to is such that a data scientist can use the Python library to build models and runs the prediction. And this library will be connected to our cluster so that it can run everything in parallel and at scale. The graphs and the result of the machine learning algorithm can be stored in our graph storage. And at the end of the pipeline, we have an analyst that can use the graph visualization tool to retrieve these graphs and visualize it, as well as to display the machine learning's results. So this hopefully will help the analyst to discover further insights about the graphs as well as the algorithms and their data. Our Python library is open source, and it contains state-of-the-art graph machine learning algorithms. My colleague Habiba yesterday gave a great introduction of the algorithms that we have in our library. So if you are interested, feel free to check it out on GitHub at stellargraph/stellargraph. Yeah, and maybe you can also do some graph machine learning for your data. That's the end of my talk. Thank you.
Wow. Wow. If that is her first talk, can you imagine what you're going to be like in 10 years? Wow, you rocked it. Well, well done. Thank you very much. That was fascinating, and it's also incredibly fascinating for me to see the evolution of graph-based machine learning over the last 20 years. I remember going to a Spark user conference in Washington, D.C. about when it first came out, maybe 8 years ago, I'm not sure. Maybe a little less. We have a couple minutes left because she did such an impeccable job with delivery. Does anybody have any quick questions that they'd like to ask Tan? No? Cool. Well, thank you so much. I really, really appreciate it, and thank you very much for your attention and for supporting through our sponsors, universities, and businesses that have supported this amazing event. Thank you very, very much for helping to bring these remarkable early career researchers and PhD students so that they could share their really interesting work with us. And you have, indeed, a bright future. Thank you, Tan. Well done.